Second derivative test for local extrema. Our objective is to use the second derivative test to find local extrema of a function. Second derivative test to find local extrema. Let f be a function for which f prime and f double prime exist on an open interval containing c and f prime of c equals 0. Remember, this means the slope of f equals 0. If f double prime of c is less than 0, think about what that means. That means f is concave down. Then f of c is a local maximum value. Put these two together. If the slope is 0 on a section of a graph where it's concave down, what does that look like? Concave down, slope of 0, that is going to create a local maximum value. Similarly, if f double prime of c is greater than 0, so that means that our function is concave up, f of c is a local minimum value. So we have concave up in combination with the slope on that interval being 0 at some point, and that's going to create a local minimum. So this is an alternative test to the one that only uses the first derivative. We find here where the first derivative equals 0, and then we plug that value into the second derivative. We get negative number. We know that we have a local maximum. We get a positive number on our second derivative. We know we have a local minimum. We could use the first derivative test. This is another tool in our toolbox. Examples. 1. Use the second derivative test to find the local extrema of g of x equals x cubed minus 3 halves x squared. Justify your answer. Because we're doing the second derivative test, we will need to find the second derivative. But the second derivative test includes finding where the slope is 0 or the first derivative is 0. So start with the first derivative, g prime of x. That will be 3x squared minus 3x. Find where this equals 0. We can factor out 3x, and we're left with x minus 1, and that gives us two x values, 0 and 1. We plug each of these into our second derivative. So we need to take our second derivative. G double prime of x equals 6x minus 3, and now we plug these into our second derivative. G double prime of 0, 6 times 0 minus 3. Now I don't care about the value. What I care about is this second derivative negative or is it positive? This will give us a negative number, less than 0. That tells me that g is concave down at the place where x equals 0. Giving ourselves a visual looks like this. Concave down at a point where the slope is 0. That creates a local max at x equals 0. So we find our local max because it says find the local extrema. Remember that local maxes and mins are the y values, so we plug the x value back in. So we have a local max, which is g of 0. Plugging it into here, that gives us 0. What's happening at x equals 1? G double prime of 1 is 6 times 1 minus 3. That'll make a positive value. Positive second derivative means the function g is concave up. Let's visualize what that is. Concave up at a place where the slope is 0, and that creates a local min. So we'll say that we have a local min, and it is g of 1. I plug the 1 into here, and I get negative 1/2. And it's as simple as that using the second derivative test. 2. Using the graph of f double prime of x below, describe the graph of f, a graph that we don't see, at x equals 5, if f prime of 5 equals 0. So this tells us that the slope of f is 0 at x equals 5. Well, what do we notice at 1, 2, 3, 4, 5? 5 is right here. What do we notice is in the graph of f double prime is that the graph of f double prime is above the x-axis. This is a positive value right here. So we have a combination of the first derivative equals 0 and the second derivative at 5 is greater than 0. That makes our function concave up, which looks like this, and at a place where the slope is 0, that makes a local min. So we can say that f has a local min at x equals 5. Thanks for watching.